Alright, hi guys. Okay, so for this video, we're given a question asking us how many molecules are polar out of these 5 given to us. Now, I already have 4 done, and I'm going to draw out OF2 for us today. So, what we're going to start with is we have the O, and then we have our 2 F's. Now, draw 2 bonds in between them, just because they have to be connected. And now what we're going to count out are the valence electrons. We're given 6 from an oxygen, and then we need to add in a 7 for both fluorines. This gives us 20. Now, we've already technically used 4. We have each bond, 2, 4. So we subtract 4, and we're final with 16 valence electrons. And now what we're going to do is we're going to add these starting from the outside, going in. So, quickly, I'm going to draw these right here. Now, I've satisfied the octet rule for the fluorines. We have 2, 4, 6. This is technically 8, 2, 4, 6. Now, we've used 12 valence electrons, 6 on each fluorine. Now we have 4 left. So we're going to fill the rest of them in. Now we have all 16 filled. These electron pairs right here are not attached to anything else. These are going to be our non-binding electrons. So now that we have a Lewis structure that satisfies all the octet rules, we're going to move on to the molecular structure. Now, because of geometry, we have our O, and our bonds are going to be down here for fluorine. Because what we have is due to the molecular geometry and all the rules that we've been given, our non-bindings go up here and push these bonds down here. So this bond right here is going to be less than 109.5. Now what we're going to do next is we're going to look at dipoles. Now, according to the electronegativity trend on the periodic table, everything going to the top right corner towards fluorine is going to be most negative. So our fluorines are going to be more negative than our oxygen. So these will be given the 2 partial negative charges, while oxygen will have the partial positive charge. This just means that electrons will drift towards the fluorine and not the oxygen. Now, net dipoles state just show that here's our electrons, and they're going to drift towards the fluorine. The arrow will always point towards the negative, and the tail end will be towards the positive. Now, this molecule is definitely polar because we have no force, no dipole going up. All we do is we have dipoles going down. Nothing cancels, so our net dipole is going to be a downward arrow. The domains are not same, so this means our molecule is going to be polar. Now, we're going to move on to the rest of the 4 out of the 5 that we've been given. Now, if the net dipoles cancel and they're same plane, everything's the same, these will be nonpolar. Now, if the net dipoles do not cancel, then the molecule will be polar. So what I've gone ahead and done is I've drawn the Lewis structures, and I've drawn the molecular geometry with the partial negativity or partial positives to show how the molecule is. Okay, so SO3, we have oxygen is going to be more electronegative than sulfur, so we draw some net dipoles. Well, some just dipoles. Now, all of these are the same with the rule that if all of these are the same in the same plane, then they will all cancel. Now, we have 3 oxygens, all different directions, but they're all the same, so they cancel. So we have no net dipole. And now, since all the domains are on this central atom and they cancel, this means the molecule is going to be nonpolar. Now we're going to move on to CCl4. drawn the lowest structure we have right here. All of them nicely play out to give themselves octet rules, and the carbon is satisfied with the 4. All of these atoms, we have electronegative charges with an with partial positive charge. Now, dipoles are going to be like this, pointing towards the most electronegative, because since they all satisfy the octet rule and all of them are perfectly fine, we're just going to go by the electronegative trend on the table. So all these cancel out. They're all the same pole. So this one is going to be nonpolar with no net dipole. All right. So now we're moving on to BeCl2. Now this molecule is linear, so the molecular geometry doesn't really affect this much. There are no non-binding electrons. So here's our lowest structure. Here's a molecular geometry. We have partial positive and partial negatives right here. So our net dipole looks to cancel because our bond dipoles go in the opposite directions with equal pull. So we have no net dipole here because all the domains are on the same central atom, they pull in the same directions, and they cancel. So this one is nonpolar. Now, final molecule out of the 5 that we're going to do today is ozone. It's O3. Now, we have partial negatives, partial positives, and this is how it plays out. Now, with O3, it's technically, this is a hybrid molecule because these down here, they share 1.5 bonds because there are 2 resonance structures. Now, they pull in different directions, and it's not satisfying for any of the molecules. They want to grab, they're not shared equally. Now, all the domains are not the same. There is a net dipole to where it pulls down, and the molecule is going to be polar. Now, we're to the final page, and we're going to revisit our question. The original question was asking how many of these molecules are polar. Now, what we went over was that SO3 was nonpolar. We did OF2, which we just demonstrated earlier on, and we decided this one was polar because they had a net dipole and not everything canceled. Now, BeCl2 is nonpolar because it was linear and everything canceled out. CCl4 did not have a net dipole. Everything was shared perfectly, so it's a nonpolar. And then ozone over here did not share things well, pulled around, wasn't happy. So overall, we have these 2. So our final answer is 2 molecules are polar. Now, going over common mistakes, what you want to do is you want to count valence electrons correctly and subtract the bonds. You don't want to have too many electrons than you need. And number 2 is look at the molecular geometry for the dipoles. You can't just judge everything perfectly by the lowest structures. And that's about it. So, bye guys.